In this video, we're going to be extending our knowledge of Python classes with a few key examples which we'll perform inside of Rhino. The first of these is going to be a famous example by Chris Langton called Langton's AND. If we go ahead and take a look at the descriptions and definitions of this key algorithm, we see that it's based on just a few relatively simple rules and understanding. So just to read this aloud for all of us to kind of get an understanding of what this is, and then we can slowly try and translate this into code using our existing knowledge from prior videos. Langton's ant is a two-dimensional Turing machine with a very simple set of rules, but complex emergent behavior. It was invented by Chris Langton in 1986 and runs on a square lattice of black and white cells. The idea has been generalized in several different ways, such as termites, which add more colors and more states. So not only is this a kind of base algorithm, which allows us to operate on what all we know so far, at least, is a square lattice of black and white cells, and then has something kind of ambiguously stated here, which is complex emergent behavior, which you can take a look at, what that may be further down on this page, and when we actually write the code. But it also has further applications to adaptations of this algorithm, like adding additional color states to make kind of more complex interactions or operations within it. And we'll actually see in some future videos how this becomes more evolved, or we can kind of add more properties or conditions to it. But for now, we're just going to go ahead and get started with one of the kind of basic premises. And, in a lot of the early computer programming, we had some kind of relationship to natural simulation. So that's what this analogy to the kind of movement or motion of an ant is. Now, in reality, is this the best simulation of ant motion? No, maybe something more complexly agent-based with some kind of response to pheromone deposits, which we now have much more advanced versions that are closer to simulating the ant motion. But this was one of the first examples, getting some kind of complex emergent behaviors in these kind of early two-state machine algorithms. Now, if we step down to the rules section, we can see that the rules for this algorithm are that squares on a plane are colored variously, either black or white. So when I read that, I think colored randomly, right? I would imagine that as colored variously, meaning colored randomly. We can either do it colored randomly as kind of initial starting points, or we can start with a full array of black values or a full array of white values for the cells. So maybe we can take a look at those as we go through this video and see the kind of differences that emerge, but we're going to get some pretty similar things happening no matter what our starting points are, and we can actually look at existing catalogs of many different iterations that have been done over the years, looking at and exploring deeply the kind of differences between start states, behavioral rules, adding more colors and state values, and et cetera, et cetera. It goes on for a long time, obviously with this being written in 1986. We then can continue on in the rules, seeing that if we arbitrarily identify one square as the ant can travel in any of the four cardinal directions at each step it takes. The ant moves according to the rules below. At a white square, turn 90 degrees clockwise, flip the color of the square, move forward 1 unit. At a black square, turn 90 degrees counterclockwise, flip the color of the square, move forward 1 unit. Langton's ant can also be described as a cellular automaton, where the grid is colored black or white and the ant square has one of 8 different colors assigned to encode the combination of black-white state and the current direction of motion of the ant. We're going to be doing this a little bit differently, and I'll explain why that is and what the differences are as we get through it. But the general idea is that since we're operating inside of Rhino, we're going to think about motion not as this kind of 8-state set, but instead as an actual vector motion in space, more similar to how we would do it inside of Grasshopper, as seen in prior videos. Now, this section below I'll just kind of quickly discuss, but we have 3 modes of behavior that come from these Langton's ants in particular. So we have the initial state of simplicity. During the first few hundred moves, it creates very simple patterns which are often symmetric. So we can see that in this example exercise with the animation of first 200 steps of Langton's ant, and we see relatively simple patterns emerging. If we look at the image above that, which is, I guess, jumping to step 3, but we start to see a different type of pattern emerging there. So then mode 2 of the behavioral modes is chaos. So after a few hundred moves, a large irregular pattern of black and white squares appears, and it appears pseudo-random. So that would be like what we're looking at in this image, primarily this kind of top patch where we see it as almost a QR code looking thing, which looks totally random. We don't see any patterns, or it's really hard to recognize patterns there. But if we look at this thing that's dropping down, or what's called a recurrent highway in this example, this is an example of emergent order, or the third mode of behavior in these Langton's ants. And we can see it states that emergent order is that third mode. So finally the ant starts building a recurrent highway pattern of 104 steps that repeats indefinitely. So all Langton's ants eventually converge to this highway pattern, and it usually happens around any time after 10,000 steps, depending on the input state. We will be able to see each of those 3 modes present when we go through kind of iterating through our ant's motion and allowing it to kind of run for that full, post 10,000 step run. We should see highways starting to emerge. So what we're going to do is take the idea or some of the logics present in this description and translate this into Python code for Rhino. If we open up Rhino, and again, open up a clean Python script, by now we should know how to do this, but Tools, Python script, and then Edit. We now have an open, clean Python file. We can give ourselves either a single line comment or multi-line comment. And we can give ourselves some information about this code. So introduction to Python classes, and then we can say Langton's after Chris Langton, Langton's ant. Okay, and now what we're going to do is just translate into a series of comments what we read from that description. So the first thing that I read in that description is that this is composed of squares on a plane that are colored variously, either black or white. Okay. And the other thing I read is that we identify one square within these cells or squares on the plane as the ant. So we have an array of squares on a plane, and then we have an ant. Okay. Then we also have the ant can travel in any of the 4 cardinal directions at each step it takes. So we could say turning or moving in 90-degree increments. Right, so we're already starting to kind of translate this in our mind, like what does the 4 cardinal directions mean? It means it could go northeast, southwest, or to think about it in Rhino space, it could go on an XY plane in the Y, X, negative X, or negative Y direction. Now, there's many ways that we can encode this in Rhino. So we could just have a set of 4 vectors, and we'll take a look at this when we actually start building it. And those 4 vectors could just be positive X or negative X, positive Y, negative Y. We definitely can do that. But in order to think kind of further down the line, we're going to make our code a little bit more versatile and start to kind of understand the basis of some more advanced computational geometry that will become incredibly useful for understanding, and it will be still a pretty simple example of how to understand that in this video. But if we are always limiting our code to such a kind of basic set that is hard coded like that, it becomes quite difficult to then kind of reuse some of those logics. So enough of that, but I just wanted to let you know that there are multiple ways of doing this step in particular. We're just going to be doing one. So you may have kind of questions of that as it comes up, but that is the reason for the way that we'll be doing it. Okay, and now to control that motion of the ant, this is the last comment that we can give ourselves. So not only do we have that kind of plane of squares or cells, and then we have one that is an ant that moves around on there, but that motion is defined by a certain set of rules. So at a white square, turn 90 degrees clockwise, flip the color of the square, and move forward 1 unit. Then at a black square, turn 90 degrees counterclockwise, flip the color of the square, and also move forward 1 unit. So we have a sequence of kind of rules and steps that we can follow in each of these, not just for the overall structure of the algorithm, but also the individual rules for the motion of the ant itself. So we have cells, we have states that can be either black or white, and this is essentially just a binary decision. So we could also say true or false. We could also say 0 or 1. All of those would be somewhat similar ways of identifying a binary set of states. Then we have particular rules related to the ant motion, which say read in whatever state we're currently at, and then based on that, do one of two different kind of reactions or responses. Make one of two different responses. So we'll leave those up at the top, and then we'll go ahead and get started with our definition. So as always, inside of Rhino, when we know we're using Rhino geometry, we're going to import rhinoscriptsyntax, and we're going to name it RS as a shortcut to label for us to refer to later on. Okay, what else do we know? Well, I'll give you a hint that because we have certain states or properties, we'll need to use and rely on our class structures. If we didn't need properties unique to a particular element or instance, then we could do this in a number of other ways, and I'm sure that there are other ways if you are clever about your coding to do this, but the easiest way is going to be to use and really leverage the power of class structures, instancing a particular instance of that class and reading its properties and making updates to them. So we can start with one class, and this class is going to be related to the squares on a plane that are colored variously. So if our thing that's moving is called an ant, the thing it moves on could be called its territory, or it could just be called its ant farm. So I'm going to call this ant farm, and then we'll tell it to pass. We don't have anything to store in there yet, so we'll just pass for now. So we've started to define our class there. We've called it ant farm, and we've done nothing inside it, so we're just passing. Now we have a second class here that is actually going to be the ant itself. So we can just simply call this ant, and right now we can also just pass on that class. Okay, now before moving too far forward inside of our Python script, we can go back to the kind of logics here and reread this and see if something jumps out to us about what type of geometry we might be starting with. So if I read squares on a plane that are colored variously, okay, let's take out for now the states. Let's take out the colored variously. So squares on a plane. What geometry has squares on a plane? Well, let's just try one. What if we did mesh plane? To me, when I read that, I think of a mesh plane, which is a bunch of squares on a plane, so faces on a plane. A mesh being composed of vertexes and then edge connections and then faces also contains the vertex list or point array, which we could use instead of faces if we wanted to for kind of easy access and translation to point geometry. So when I read that first line, I think mesh plane. So we'll make the assumption, at least for now, that a mesh plane is the best geometry here. It has all of those properties within it. Okay, so if I go ahead and delete that arbitrary mesh plane, what we can do to start is type mesh plane, hit enter, and now we're going to start this at the origin. So I'm going to type 0 for the first corner there, and we're going to use that x and y count of 100 and 100. So if you didn't have that set, then you can go back to that first step, make the mesh plane, set x and y count to 100, and now place the mesh plane at the origin, and we'll just type a length and width of 100 each. And now we get a distance between each point of exactly 1 millimeter, or whatever your Rhino units are. So in mine, it's 1 millimeter. I'm gonna hide that grid so we just see our mesh plane. So we're looking at this mesh plane. We have a density of 100 by 100, and it's also 100 millimeters wide and long, meaning each vertex is 1 unit away from each other. That's going to be enough, so that's all we need to set up for the mesh plane, which is going to become our ant farm. So when we're setting any geometry from Rhino inside of Python, we need to use getObject to bring it from that Rhino document into our Python script. Before we go ahead and do that, since we're incrementing in steps here, I'm going to just copy all of, we'll copy the comments as, actually no, what we'll do for this is just leave the comments at the top just to keep it kind of clean as we iterate through. We'll give ourselves a break comment here just to keep things separate. And then we will paste this and comment that code out. Below our two class constructions, we are going to want a way of bringing in this mesh plane. So as I mentioned, we're going to use rhinoscriptsyntax getObject. Well, getObject takes an input message, so we can say select the farm. And then since we know we're going to use a mesh plane, we can also filter by mesh. Okay, and now if we click play here, we can select the farm or select that mesh plane in our Rhino document. And if we print this, we can also see what this is doing, which is grabbing the GUID of that mesh plane and placing it inside of our Python script, which is perfect. So now we have a reference to that plane. If we want to read this into our class, what we need to do is first construct an instance of this class. So we're going to name this my ant farm, lowercase m, and then capital A, and then F. And we're going to set this equal to an instance constructed of that class ant farm. Now, since we want the actual mesh we're reading into Python to be our ant farm that we're reading, we're going to need to pass this into our ant farm class. So I'm going to cut that from line 45 and pass this into our ant farm. To pass in any information into a class, we need a constructor function. So we need to replace this pass with def underscore underscore init underscore underscore. Then we know we always need to pass in self, so we're going to pass in self, and then whatever variable we want to read in that getObject function, so that GUID into our class as. So I'm going to call this mesh ID. Then I'll close that parentheses, hit colon, and hit enter to tab into our constructor function. As in the previous video where we introduced classes, here is where we're going to store the properties of this particular class, which is our ant farm. Well, what do we know that we both have and need? We know that we have a mesh ID. We know that we need some array of cells. And then we also need an array or a list of states for each one of those cells, because each one needs to either be black or white. Okay, well, first we have a mesh. So let's just make a variable for that mesh. Let's call it self.id equals that variable mesh ID. Now, what else do we need? We need an array or grid of cells. What can be considered an array of cells inside of a mesh? Well, we could use faces, but another way of doing it is to just directly use the vertices. So we're going to use each of the points on the mesh, because that way we don't have to take the centroid from the faces. We can just operate directly on the grid of points. So we'll just think of this as a 2D grid of points. To get vertexes from a mesh, we need self.vertexes. So this is just going to be the variable name that we call this, a list of vertexes. And then we can access our rhinoscript library and type mesh. If I scroll down here, we can see all of the operations for meshes. So we have faces, face vertices, we have face centers. So we could structure this with faces and face centers, and we could just use it that way. Alternatively, we could just use the vertex lists themselves, and there is a reason why we're going to do this, and I'll explain that later on, but I'm going to give us a hint that we're going to just use, for the sake of ease, our vertex list instead of our face list. So in that case, we want to go to mesh all the way down to vertices, hit enter, open parentheses, and let's take a look at what this is. So it takes an input parameter of an object ID and returns the vertices of a mesh. So that's going to be the grid of cells or grid of points in that mesh. Okay, so what does it take as an input? An object ID. Well, where do we have that stored? We have it stored as self.id. Alternatively, we could also just use directly the mesh ID. Doesn't matter, but we'll just say we'll use all of our, once we've stored anything as a variable inside of our classes, we'll always refer to whatever that property is inside of our class. So self.id gets passed into rs.meshVertices to give us a list of our vertices. Now we need states for each cell. So we can call this list self.states, and we can just make that an empty list. If we know that we wanted to start with a certain value for each of the points, so in the example, it says colored variously. So that might mean that we need a random value stored. So a random value, either 1 or 0, a random state, black or white, true or false, stored inside of our states. We know that every cell needs to have a state, so the length of both of these lists needs to be the same. One way of doing this is saying for I in range length self.vertexes, right, looping through that amount of times, and then not making an empty list every time, but making an empty list self.states, and then saying for I in range length self.vertexes. So for the length of that list, we can use self.states.append some value here, which we can say is 0. Or alternatively, we could say is false. So let's start with true and false, but we could do 0 as well. So let's start with true and false. Self.states.append false. So that's going to start by appending false states to every single vertex or every single cell in our ant farm. So we start with all black cells. Let's go ahead and do that first. Alternatively, we could flip this to true. We could also start with random states, but let's go ahead and start just with all false states. Before we get to the next stage, I'm going to copy this, comment it out, hit enter a few times, and then paste here. So the next step is to build out some of the functions and properties for our ant. So how can we define this ant? Well, if we have a grid or array of points or vertexes in our mesh plane, then we can also just say our ant is just one of those points on the plane. How can we define that? We could just define that by a point in space. So we could just drop a point in space. How do we get that into our Python script? Well, we say rs.get object. We can give ourselves a message to select the ant, and then use a filter of point. Now when we run this, we would be able to select our point inside of Rhino. To be able to use it in Python, we want to store it as a variable, which we can just say point, because right now it's not actually an ant, because we're not actually using the class ant. So right now we'll just say we're reading it in as a point. So I guess technically here may be deceiving, but it will become the ant. So point equals rs.getObject. So now if we click play on this script, we're missing a parentheses on line 78. So I didn't close off that range parentheses. Now if we hit play, it's asking us to select our farm, which is our mesh plane, and then the ant, which is our point there. Great. Nothing's happening because we're not making any print statements, and we're not changing any geometry. But we are also not getting any errors. So we've read in that point. Now, what are the properties of the ant that we care about? Well, we know we care about the position relative to all of the grid or array of points on this mesh plane. We also care about the direction because we have to turn it, right? That's in the rules, we have to turn it. How do we correlate also one particular item in space with a list of other ones? Well, or refer to, let's say, the closest point within that whole list. We do it like we would refer to an item in any list, which is through a series of indexes. So that means we have a position that we care about, we have a heading or vector or velocity that we might care about. Then we also have the index in the array of all of our grid or states. So if we already know those, then we can go ahead and make a constructor function where we pass in that information. So we always start it with def underscore underscore init underscore underscore open parentheses self comma, and then we can feed in those three variables. So pos, vec, and index. Now inside of here, we can just translate them to properties of our ant. So self.pos equals pos, self.vec equals vec, and self.index equals index. Now we just need to translate our point that we're reading in into variables to be able to pass in and instantiate that particular ant. So we'll say we need a position, not the point itself, right? We don't want the GUID, we actually want the three coordinate values, the x, y, and z. So we'll call this the location. Alternatively, we could call this pos, but we're feeding in pos. So let's call this the location, LOC, and set this equal to rs dot point coordinates, which if we open up says it takes in an object ID. Okay, we have an object ID, which is our point ID. What does it return? It returns the x, y, and z coordinates. That's what we need. We need that location, not the point itself, which is great. So we can just feed in that point into our point coordinates and get a location x, y, and z. And if we print this, select our ant farm and our ant, we see that our ant is located at 4747, 0. So that's the particular location. Okay, now how do we coordinate this location with a place or a point on the mesh? Well, we can use the rhinoscriptsyntax function called point array closest point. What does this do? It reads in a list of points. We have a list of points, which is the ant farm self.vertexes. What else does it read? A test point to test the location from. What does it return? The index of the element in that point list. Exactly what we need. We need the index to reference the self.vertexes. What do we have? The self.vertexes, which we can feed in as that list of points. What do we need to feed in here is the test point, which we can give as the location. We can store the output of this, which is that index, as a variable called index. And then lastly, we need a vector or a heading for the ant, which we're going to just say is the next vertex from wherever we are currently. So wherever we're placed in our ant farm, get the next one and make a vector from that. So we'll use the rs.createVector to make a vector in space. What does this take? This takes in an x, y, and z input value. We want the point next to this, or the vertex next to our ant's current location. So we know that the current location exists at index. So if we wanted to know, what that index is, we could say print index. I'm going to comment this line out for the vector for now. Hit play, select our farm, select our point. We already have an issue because we've accidentally referred to self outside of the class. So it's not self, it's actually this particular instance of the ant farm. So my ant farm equals ant farm, that's a particular instance. We're referring to the one that we've selected, which is my ant farm, that's what we've named it, and we want that ant farm's vertices. So we need to call it my ant farm. We can't call it self outside. Now if I hit play, select the ant farm and then the ant, we get an index value of 4,794. Now what if we don't want the index value, but we want to figure out in this list what that actual point location is? So what are the x, y, and z coordinates? So we can give the entire list, and then to receive or retrieve one item from that list, we open up brackets and then place an index inside of it. So now if we click play, select our ant farm and then our ant, we get 47, 47, 0, which was the exact same value as our location that we got from our point coordinates above. That's great. Now what we need is not this index, but we need the next index, which would be index plus 1. Now if I click play, select the mesh and then our point, we get 48, 47, 0, which is just 1 in the x-axis. Now we could make this any random vector or whatever we might want to start on. In this case, we're just going to start it heading 1 unit in the x-axis. So it's headed that way, and then we can apply the rules to turn it. So to get that next vertex, we use that index plus 1. So if we uncomment our vector here, to create this vector, if we want the vector from our current location to that next vertex, we can do point subtraction, which is the goal point minus our current location. That gives us the heading vector. I can prove this by just, again, I'll comment this out again just so we can prove this out, printing our goal location, well, that's our next vector, minus our current location. Hit play, select our farm and then our point, and we get a vector of 1, 0, 0. Alternatively, what we could do is just directly feed in a 1, 0, 0 vector. So either way is going to work perfectly fine, but this is where a more robust setup that will work in the future for different examples is going to be to directly use the vertex list and find the next one in that list. So here where we're declaring our vector, we can say vector equals that subtraction and then close our parentheses. And we can comment out both of those print statements. So that gives us a vector of 1, 0, 0, which is a vector 1 unit long in the x-axis. Now we just need to instantiate our ant class by calling it ant and then feeding in those variables. So we have LOC, comma, and then our next one is our vector input. So we're going to feed in vector, and then our next one is index, which will feed in our current index. We've instantiated it, but if we want to actually refer to it, we need to save this as a name, which we can call my ant. So my ant equals that particular instantiation or instance of the class ant. I'm going to copy all of these lines, comment them out, and then we will paste those lines again below. So the next step is now to actually do something with this information, or do something with the kind of setup that we've built here. What are we going to do? Well, we need to move our ant in space. If it didn't move, then we would never have any change to this, and it wouldn't be a particularly exciting algorithm. So we can do this by adding a function inside of the class ant, which we're going to call moveAnt. And we need to feed in self, as we do with all functions inside of our classes. So move_ant, feed in self, and inside of this function, we need to do a series of things. The first is read the state of the closest point in the ant farm cell list, or vertexes. Next, we need to respond to that. So if that state is white or true, turn clockwise. If black or false, turn counterclockwise. Next, no matter what these states are, we need to flip the state and then move forward 1 unit. So we know that those are what we need here. We can just now go ahead and pass in there until we infill some information to be able to run that particular function. Below the instantiation of our ant, if we want to run that function, we need to call it outside of our class, and we can call any function by referring to the instance name, myAnt, period, and then the function name move_ant, open and close parentheses, assuming we don't input or take in any data or variables inside of that function. So myAnt.moveAnt, and that is all. So that gets us started with a base structure for that move function. Now we can go ahead and copy these lines again, just to have this broken down into steps so that we can understand and refer back to it later. And just hit enter a few times and then paste back in. So now in this stage, we're going to just infill the actual operations inside of our move function. So we can start with this first comment here, read state of the closest point in the ant farm cell list, vertexes. Well, what is the closest point and how do we refer to it inside of a list? We can refer to it by referring to our ant farm class, or the instance of it, which is myAntFarm, accessing the list, so vertices in this case, let's say, and then using the index value that we've stored above. So if we want to start, we can first start by referring to that particular class, myAntFarm. And if we want let's say, vertexes, so we're accessing that list vertexes, and then inside of that list, we're going to use index. But because the index is now stored inside of our class, and we want to refer to this inside of our class, so this property of this particular ant, we don't use index, we instead use what we're storing in our constructor, which is self.index, to refer to the particular index inside of this class. So myAntFarm.vertexes, and then of self.index. If I print this and we hit play, select our ant farm and then our ant, we get 47, 47, 0. So it's printing that location or point, which was the closest point from our ant point to the points on the mesh. Well, we don't want the actual point, but we want something close to this. We want the state of that closest point. Well, we did structure a list up here when we constructed that ant farm of an empty list of states. We filled in for every single item in self.vertexes, which another way of doing this, actually, if we look at this loop, this might even be easier to conceptualize, is not looping through for the length of that list, but for every item, for item in self.vertexes. So for each item, store a value or append a value of false. So if we want to access the states, all we have to do is use that exact same index, because they're stored with the same index values. And we just need to say not dot vertexes, but dot states. And now if I hit play, select our ant farm and then our point, we get a false value, which right now all of our values are false, but we're actually returning or retrieving the state of that particular index. So we want to use myAntFarm.states self.index. And we can store this as a variable, which we'll call state. So that's the current state of this ant. Now what we need to do is perform some response based on that state. So let's say if state, meaning if it's true. So if state is true is the same as saying if state. We can leave it in long form just so we get the idea of it. So if state is true, then what do we want to do? Well, we want to read in the current position and rotate it 90 degrees. How can we rotate that? Well, we can use rs.vector_rotate, which is a rhinoscript function which allows us to rotate vectors in space. What does this take? It takes an input vector. So we have self.vector is a property that we already have. This should be not capitalized. So self.vector. So we'll rotate the vector. What else does it take? An angle in degrees. Okay, so a number in degrees and then an axis. Well, what is our number? Well, we know we want it to rotate clockwise, and we want that to be 90 degrees clockwise to keep it on the cardinal directions. So self.vector, rotate it 90 degrees. And now we need an axis here. Well, what is an axis of rotation? If we want to rotate it in the XY plane, we can look with our kind of hands to understand the axis of rotation relative to the rotation itself. So if we curl our hands slightly, wherever our thumb is pointed is the axis of rotation. So if we do that and we rotate counterclockwise rather, the up axis here is showing us that our 90-degree rotation is going to be counterclockwise if our axis is the up axis or the z axis. So it's our vector rotated around the z axis. So we can just say 0, 0, 1, which gives us a vector which is vertical. So 0, 0, 1, the z axis vector. Now we don't just want to rotate that vector, but we actually want to rotate it and keep that as our current heading. So to do that, we need to overwrite self.vector and set that equal to vector rotate. Now we can go ahead and print self.vec. And just to test this, let's change this to false because we know that the state is false. So let's just test this with a false value here and see what it prints. So I'm going to hit play, select our ant farm and then our point. And we now get a rotated vector of 0, 1, 0, going from the x now to the positive y, rotating counterclockwise 90 degrees. So that's exactly what we want. We can now change this state back to true. So if the state is true, rotate the vector, save it as that new heading. Okay, so we've done that turning. I'm going to comment that printout. Now, if it's false, which we actually don't need anything more than just an else statement, because if it's not true, then it is false. And now we want to do the same exact operation here. Still the same axis, but we want to turn counterclockwise. So actually, we flipped this here. So we've actually turned counterclockwise using a positive 90. According to Langton's ant, it's not going to matter too much, but according to Langton's ant, we actually want that to be clockwise, and we want our false values to be counterclockwise, which is a positive 90 degrees. Again, you can determine that with using your thumb as a kind of idea of the axis. So if it's pointing up, our hand rotates where our fingers are pointing, which is counterclockwise. So that gives us an idea that positive rotation value is going to rotate counterclockwise. So now If we printed this, we would see, just like we did before, that we're getting that counterclockwise rotation. The value is in fact false, so we would see that it's running the false one and not the true one, and it is rotating counterclockwise and not clockwise for our true value. Now the next two steps, flip state and move forward one state, we could perform this flip state after, since we have to do this no matter what. However, we want to be able to read in what the current state is to know what to flip it to. If it's true, we don't want to flip it to true. If it's true, we want to flip it to false. Well, if we have that type of conditional, why not actually just nest this inside of both conditionals so that we don't have to rewrite it? So why not say here, my antfarm.states self.index, so the particular property at this location where we currently are needs to flip, so it equals false. If it's true, it now equals false. We can copy this line down into our else statement and say else, meaning it is false, flip it to true. So we've now done the rotation, flipped the state, and now the next thing to do is to move forward one unit. We could use a move object, or if we don't want to do it in that particular way, moving a point in our Rhino geometry, we could also just use vector math to use a vector added to a point, which gives us that moved point. So if we have a point here, 47, 47, 0, and we added 1, 0, 0 to that point, or a vector of 1, 0, 0, it would move it 1 unit in the x-axis, which would then give us a point of 48, 47, 0. So adding a point in a vector gives us the resultant point moved relative to that vector. So that's why in moving an object, we just use a translation vector. It's basically just taking that thing and moving all of the information at that vector. And with points, it's even easier because we can just actually directly add them together. So we'll use a function called pointAdd, and it will take in 2 points. So we can go ahead and just add in self.pos, our current location, plus the movement vector. Now, since we want to always be referencing this back to our ant farm, we also need to update our index. So we've moved our position. We also want to know where is that in our ant farm. So where is our ant moved in our ant farm? Well, the first thing we need to do is make a variable to call or to store this added point information into. So our new point location, which we can say is temp pos, set that equal to rs.add, our rs.pointAdd, which is going to add those 2 points together, one being a vector, but we can consider it a point, an x, y, and z value. And then we need to update our self.index, the index value that this current ant is on. So self.index, set this equal to the same thing that we have here. So rs.pointArray closest point, myantfarm.vertexes, but instead of LOC for location, we need our temporary position. Why are we using a temporary position here? Because we don't want our position, our self.pos, to be this specific addition. We want it to be exactly where this self.index is. Oops, I have an extra index there on that line. So we want it to be exactly wherever this self.index is. So now to finally update our actual position, we can say self.pos, meaning this ant's position, equals myantfarm.vertexes input index. And we could just use index, but I guess since we're storing it in self.index here, let's just refer to it as self.index from then on out. So self.index. Now I can delete this pass, and we're actually updating our ant. And now when we run this move ant function, we're going to read in, check all the states, find the current state, read whether or not it is true or false. If it's true, perform this clockwise rotation and flip the state. If it's false, perform the counterclockwise rotation, flip the state, and then update our current position, moving forward 1 unit in that new direction, so that turned direction. So if I click play, click on the mesh, then the ant, we get no information output right now, and that's just because we don't have any print statements. So we could go ahead and check this by just printing self.pause. So right now we're at location 47, 47, 0. If I hit play, click on the ant farm, and then the point, we're now at 47, 48, 0. That is because our state is false. We're then creating a vector that is in the y-axis 1 unit. We're adding that to our current location and moving, which means we move to 47, 48, 0. So that is our current location. And we would then be updating our index as well. So what can we do here so that we don't just have to print this every time in order to output information, but what if we wanted to actually color directly the cells on the mesh plane so that we got some feedback information for us to be able to see what's actually happening? Well, we can do this with what we're going to call a render function, which is just a custom function we'll add to our ant farm. And we'll use the properties of a mesh, which allow for each of the vertexes to be colored, and we can then visualize the colors of each of those vertexes. So below our move ant, we're going to access the instance of the class myAntFarm dot render. And actually, before we do this, I just want to select all of these lines just for consistency's sake, comment them out, and then we'll step down a bit, paste. Okay, and now we'll get into this render function. I'm going to delete these 2 print statements as well. Okay, now we have a nice clean bunch of code, and we can go ahead and make this render function. So myAntFarm to refer to the specific instance of that ant farm dot render, open and close parentheses. So that's all we need to refer to that particular ant farm function or method called render. Now to make this an actual function, we need to go up to our ant farm, tab out of the constructor function, and we need to make a new function called def render. What do we need to do every time we make a function inside of a class? We need to feed in self so that we can access the variables or properties stored, as well as other functions stored inside of that class. Now inside of this, what are we going to do? Well, we need to create a list of colors based on the state values, and then store colors as vertex colors on mesh. So that's all we need to do in this. It's as simple as that. If we're creating a list, what do we need? We need the name for that list, colors, and we need to set it to an empty list. If we need to check the states, what do we need there? We need to be able to iterate through or loop through all of the items in that. So we can say for state in self.states, referring to the current self.states that we've stored up here. So for state in self.states, if state, meaning if it's true, colors.append rs.create color. So we can actually make, using our create color function, a color using RGB data. Now, RGB color information is on a spectrum from 0 to 255, where we have all 3 R, G, and B input values. So we can see this here where red index is 0, green index is 1, and blue index is 2. And then we do have an alpha value, but we won't get into an alpha value right now. So if we want to access the R, that's the first item. So if we wanted, let's say, a red color, we would say 255, 0, 0, giving us the color red. If we wanted a green color, we would say 0, 255, 0. And if we wanted blue, we would say 0, 0, 255. R, G, and then B are red, green, and blue. Now, if we want black, that's going to be the absolute absence of all colors, so 0, 0, 0. If we want white, it's going to be the presence of all colors, 255, 255, 255. You're welcome to use any colors that you would like to render this. We're going to start with the black and white color values, so 255, 255, 255. The actual colors do not affect the states themselves, they're just a visualization of them. So just keep that in mind. It doesn't matter what color we're using. So once we've created that color, that particular one color, we're appending that to our list of colors. So for each item in states, we're going to have one color value related to that item. And we're adding that color value based on these conditionals. So if state is true, or else, if it's not true, then add a different color. So colors.append rs.create color again. And this time we'll use 0, 0, 0. And close out our parentheses, hit enter, and now tab out of our loop. So now what's next here? We just need to store colors as vertex colors. So if we type rs.mesh and then cycle through this list, we should be able to find something related to vertex colors. So we have mesh has vertex colors, which gives us information about whether or not it has vertex colors. Let's keep going, see. Okay, and here we have mesh vertex colors. So if we just hit enter, open parentheses, we can take a look at what this takes in and what it gives out. So it takes in a mesh ID. Well, we have a mesh ID. That's going to be called self.id. That's the mesh we input. What else does it take in? Colors. Okay, what does this say? It says a list of color values. Note for each vertex, there must be a corresponding vertex color. So this is going to color vertexes using corresponding colors of equal size lists, which is a good thing that we're using our states here and that our states are exactly the same length as our vertices. Otherwise, this wouldn't work. So we've appended the same amount of colors as there are both states and vertices. So we can just go ahead and use our colors list. And now if we close the parentheses there, we can take a look at what it returns. It says, if colors is not specified, the current vertex colors. If colors is specified, the previous vertex colors. Now what we're going to see here is that it actually colors the mesh in our document when we run this render function. So it's applying the colors that we're reading from each of the states or developing from the conditional related to the state values. And we're applying that all in one function. So all of the colors all at once from a list of all of those colors applied to all of the vertices in the mesh. Now we're coloring that entire list one time, running that function render at the bottom here. And when we click play, select our ant farm and then our point, we can see that every single vertex is black because that's what the starting values that we're using currently. And we have one vertex that is white. Why do we have one vertex that is white? Because we've run this move ant function one time. What does that move ant function do? We've run it also before the render. Keep that in mind. So we've run it before the render. What does that function do? Well, it flips the state value. So it flipped that 1 point value. What if we ran the render function before and after that move function? So let's click play, select our ant farm, and then our point. This is going to be quick, so we have to look very carefully. And you can see it barely, but you should be able to see it flicker, which means it goes all black and then quickly changes that state to white in the middle where our point is. If we move this point somewhere else, we have a leftover of that vertex color, but we can click play, select our ant farm, and then when we select at this point, all of the vertexes will go to black, and then that 1 point will flicker and change to white. which we can see it update. So it's reading wherever the closest index or closest point value is to our point that we're selecting. Now, what if we want to perform multiple actions, or we want this to iterate through multiple times so that we can actually see types of emergent behavior as was described in the Wikipedia page? Well, let's just go ahead and select all of this, comment it out using Control and /, and then paste these lines in. So we don't need to render at the beginning, but instead we want to perform multiple movements. So let's use a for loop as we've done previously. So for I in range, we can start with 10. In order to perform this action or run this function within this for loop, we actually need it in the tabbed space. So for I in range 10, run this function move. And if we just left our render outside of this function, it would not run 10 times. It would still just run once at the end. So if I click play and then select our ant farm and then select our point, we see it running 10 times, but it's only rendering once. Instead, if I tab this in and have both functions running inside of our loop, we'll get both functions running 10 times. Now if I click play, select our mesh and then our point, we'll see it loop through. If we increase our range to 100, click play, select our mesh farm and then our point, we can see that point running 100 iterations, so 100 steps. We could also run it for even longer, let's say 1,000. So those first couple of 100 steps, we did see that kind of simplistic or symmetric behavior. And then as you get into the kind of 100+ range, you start to get more of that kind of randomness that will show up. And then once you get into the 10,000+ range, you'll start to see properties of emergent order. Now, in order to not bog down our Rhino visualization, once we start getting into a range of the thousands or so, which we're starting to see some kind of random patterns emerging, what I would recommend is probably saving this render function and stepping it outside of the range. And now we can go up not to 1,000, but to 10,000, hitting play, and then we can test this out on 10,000 steps where we should see some of those highways starting to form. Select our ant farm and then our point. And now very quickly it renders that. So we haven't quite seen it yet. Let's go a little bit further. Let's go 11,000. Hit play, ant farm, and then our point. There we go. And now we see our highway starting to form. And we would actually see it continue to extend because once this pattern is formed, it continues on indefinitely. So it'll continue this exact pattern within, I believe it was like 100, I think it's like 97 steps or something. And that pattern continues all the way down in this axis or direction. So the next thing that we can try and do with this script, again, copying all of this down and commenting it out, is to not just have one ant input, but instead add multiple ants. Well, how do we add multiple ants? The first thing we need to do is say, instead of point, we need to input points, getting points, selecting ants, plural, and then we can filter points. So I now have one point drawn out here. If we copy these all around, maybe moving them so that they're not in such a symmetric pattern. There. So we now have 5 points drawn out in space. When we run this script, we'll run get objects, prompting us to select multiple points there. We can then select all those points. But all of these input variables to our ant are all singular. So how can we run through the multiple points that we're selecting? Well, what we can do is say for point in points, stepping through each point in our list of points. Now we can nest these all inside, and we don't even need to change that point call because we're still using point as our variable stepping through. So it's going to go through that entire list of points we've selected and step through each individual point. So this works. However, we're still only feeding in 3 variables into our ant. What if we want multiple calls to this function? Because we now need to have 5 different instances of the class ant running on the same ant farm. Okay, well, we already only have one instance of the ant farm, so we'll leave that. What if we want multiple ants though? Then we need this ant instance or call to that ant instantiation inside of that loop as well. But we're overriding the variable here because we're calling it my ant, and then every time we're referring back to my ant. So then that would only move one of the ants, which is the last one in the list. So this doesn't quite work. Actually, what we need to do is be able to store all of the instances inside of a list, which we can call population. So this list, population, is not going to be equal to the ant instantiation. We are going to append that instance of the class ant to the population list. Now we need to actually make this population list, which we can just set above that loop. So population is an empty list first, and then every time we construct an instance of the class ant, we append a new ant to that list. Well, now what about our loop? We now no longer have something called my ant. Well, easy enough. We can just say in each step of the iteration, because we don't want to iterate for each individual ant 10,000 steps separately. We want to iterate for each step through every single ant, right? So we want this to be our main loop, and then inside of that we want another loop, which is for my ant in population. And let's just go ahead and capitalize population as well. So for my ant in population. Now we just need to tab in the call to move the ant. And that's going to take each ant at each step and run them all in our mesh. Now we can just go ahead and click play, select our ant farm, drag across to select all of our ants, and hit enter. It's going to take a second to think, but then we'll see the output render show up. So now we have emergent highways from multiple ants that are actually getting disrupted when they run into other ants. If we want to visualize this, we can step this render function all the way in, but then we need to lower this value back down. So we'll say 100 steps, step it all the way in, and this is going to render every single ant moving every single time. So if I click play, you'll see what I mean, which is we'll see the entire thing go black, and then we'll actually see each ant moving separately because this render function is nested inside of the loop through each of the ants in our population. So hit play, select our mesh, ant farm, select all of our ants, hit enter. And it's a bit hard to tell, but they are alternating. So they're not moving all at the same time actually. So now we get that output there. If we back up our render one step and leave it just inside of the main for loop, then it will just render one time for each of the 100 steps. So it's not going to render for every ant, which would be 500 times total because it's 5 times the 100 steps. It's just going to render for the each of the steps of the main loop. So if I hit play, select our ant farm and then our ants, we get it running much faster, and we see all of our ants interacting in space. We can try and go a little bit higher, maybe 400, play, to see if we can see interactions happening between these. Because they're now going to start affecting each other's territories and adjusting each other's states based on that kind of state affection. So it looks like we're still not getting overlaps there. We can try and just move these points closer together and see if we can more clearly see how they react to each other then. So now play, select our mesh, and then our points. And now we can kind of see them interacting there and building in this kind of distorted version of the territory. And then we get a resulting mesh colored as such. And finally, if we, just as we had before, back that render function all the way out, then it allows us to run for the total 10,000 steps, or we could even do 20,000 steps. That is 2,000, 20,000 steps. And then we can hit play, wait a moment, and then once it's finished processing, it will render. We can also switch to rendered view so that we don't see those lines there. Hit play, select our ant farm, and then our ants, hit enter, and then wait for it to compute. So it looks like actually our mesh plane here is a little bit too small for the 20,000 steps for that emergent order to show up. Well, how can we change this? We can give it a bigger ant farm. Let's make a mesh plane starting at 0, not with 100 count, this time 1,000 count, and 1,000 count, starting at 0, that is 1,000 by 1,000. We still have a unit size from vertex to vertex of 1. And now if we click play, we can select that larger ant farm, select our points, and hit enter. And then just wait for it to compute. So for that example, it looks like our timing was a little bit high in general, just because it took a while to wait for that. Because keep in mind that now it has more vertices to cycle through. There are other ways of kind of speeding this up and making it a more efficient process when we have a kind of larger search space like this. So if we want to limit it down to, like, let's say 1,000 for now, then we could move these points in space, because it looks like they were also quite constrained in that bottom left corner. And then since we don't have a kind of toroidal search space, meaning once they kind of hit the bottom, they hit the bottom. So we're not actually looping them up to the top. We could do this, but if we're not doing this, then we end up just allowing them to kind of die into the corners. So if we wanted to, we could do one more check just with them in the middle of this larger search space. Select the farm, and then the ants, and then hit enter. So we can see just a small patch, but since it's within 1,000 iterations or 1,000 steps, we're still getting that kind of just start basically of the chaotic behavior. And then we would see chaotic or kind of random pattern behavior for until the 10,000th step around there. And then post 10,000, we would start to see these kind of highways emerging. So this is probably too dense of a mesh to really be able to quickly process and show these examples. So maybe go a little bit smaller, but test out different size meshes, different point locations. Also, instead of covering it in this video here, I'll kind of end this video as a prompt for a few suggestions on how you can update this. So this is the basic algorithm using multiple ants inside of one singular ant farm with just binary state changes, so true or false state changes. So one way we can improve this, or at least add to this, is creating multiple states and then having multiple conditions for each state. So what if instead of black and white, there was a spectrum of 8 values of gray? And if it was within this certain 8 values, or let's say even better, maybe R, G, and B. So what if instead of just red, instead of black and white, we did R, G, and B, red, green, or blue? And that came with 3 conditions instead of just the 2 that we have here. What if it's, maybe one is go straight ahead, one is turn left, and one is turn right? Well, what type of effect does that have? And there's some examples online where you can see how these are structured, but maybe just give it a go thinking through how you would adapt this code to that type of scenario. Additionally, what if we did want that kind of toroidal space where it started to wrap on itself, meaning once it gets stuck at the bottom, it actually goes up to the top and then continues on. Think a kind of 80s Pac-Man where they move through the screen, and then once they kind of hit the left side, they end up coming in again from the right. So how would you start to set that space up? I'll give you a hint there. It has to do with the way that we've set up our vertexes and our indices and how we're actually calling these vertices. So if we get stuck here, that's a particular index. Well, if we want it to pass up, we need to give some augmentation to the index value to tell it to go up to this index. This mesh is relatively structured in a 2D array. So we would be able to kind of make certain assumptions to calculate the index in order to do that, and then find the nearest index up there. So we can make an adjustment between the vector and position, as well as the kind of closest index point, making that adjustment to be able to create a toroidal space there. Lastly, how would you adapt this to not run on a 2D plane, but actually run on the surface of a mesh, right? We took a look at mesh geometry, so what about a mesh sphere? How could we adapt this code to run on a mesh sphere? I'll give you a hint for this as well. Right now we're limiting our vector rotations and motion to just 2D. So we would need a different axis of rotation, that's for sure. We would also need to kind of constrain our vectors to the surface or somehow related to the surface of the mesh. We then also make sure to be snapping like we are now to the exact indexes or vertices of the mesh, but we need to ensure that that vector can actually allow for three-dimensional motion and that we're getting close enough to the other vertexes to be able to move and snap to those. One way that we're going to take a look at in future videos related to these class structures is to actually be able to use what are called the mesh topology vertices, which is the kind of connective tissue of the mesh. So all of the mesh vertexes and their connections. So we're going to be able to use some properties from things like that to actually tell us what our neighbors are, and then make decisions to move, based on what our neighbors' properties might be. So that's going to be something somewhat similar to what we have here, but that gives you a hint on how you might start that. So starting to kind of tailor motion in 3D, and then maybe based on mesh neighbors and not just a kind of arbitrary vector in space, and then tying it back to the mesh vertices. That's all for this video, and in the next video we'll get into another classic example of Python classes, investigating the idea of cellular automatons.